How can we generalize the idea of Edmonds matrix from bipartite graphs to general graphs? The answer is given by a so-called Tutte matrix of a graph. This matrix is also symbolic, just as Edmonds ones, and it generalizes the adjacency matrix of a graph, so that now we assume that we have a graph G on n vertices. It no longer needs to be bipartite. And then the Tutte matrix for this graph is defined like this. In the adjacency matrix of this graph, at position ij, we would put 1 or 0 if vi is adjacent to vj. In Tutte's matrix, we would put xij here just as in Edmonds matrix, but if I is less than j. And we have a symmetric position in the row j and column I. And in this position, we would put minus xij if vi and vj are adjacent. So we see that this matrix is skew-symmetric. If we take its main diagonal, then the entries on both sides of these diagonals are negatives of one another. The transpose of the matrix is minus the matrix itself. Now, unfortunately, unlike in the case of bipartite graphs and Edmonds matrix, we cannot say that there is a direct correspondence between a matching in our graph and a term in the determinant of the matrix. Consider an example when our graph is, say, just a path of length 3 on vertices v1, v2, v3, and v4. Then the Tutte matrix for this graph would be x12 minus x12, x23 minus x23, and x34 minus x34, and all the other entries here will be 0. And now if we consider a transversal of this matrix, one of its transversals, we see that we have a transversal like this. Elements standing in different rows and different columns of the matrix. And this gives us x12 squared times x34 squared. Well, if we take the corresponding edges between vertices 1, 2, and 3, 4, they indeed form a matching here, but we have squares here. And if we consider a cycle graph on 4 vertices, a graph like this, and its Tutte matrix, then we would also have entries like x14 and minus x14 here, and one of its transversals would be this one, which is x12, x23, x34, and x14 with minus. And this term actually corresponds to all the edges in our graph. So at first it looks like everything is lost. So the structure is not here. We cannot relate immediately these guys to nice matchings in the original graph. But it turns out that although now each term cannot be in one-to-one correspondence with a matching in our graph, still the same proposition can be proved. The determinants of the Tutte matrix, which we again will denote by A, is identical 0 if and only if there does not exist a perfect matching in G. And we shall now prove it. So let's look at the determinant of our matrix. And let's look at the non-zero terms of this determinant. Each of these terms corresponds to some permutation P. And recall that permutation has some cyclic structure. So we can take numbers from 1 through n and see where the permutation takes 1 into some p of 1. Now, where it takes p of 1, and so on and so forth. So if we build this kind of directed graph representing the permutation, the out degree of each vertex is 1, the in degree is 1, so this is just a collection of cycles. So the permutation itself corresponds to a bunch of disjoint cycles over an n-element set. Some of these cycles may actually be loops, if some point is a fixed point of permutation. Some of these cycles can also be somewhat degenerate, so just cycles of length 2, where permutation acts as a transposition of two elements. so that we can have different cases here. And now if we look at a permutation P for which this guy is non-zero, what does it mean? As in the graphical structure of our permutation, we have an arrow from every I to P of I, and we have a corresponding term here, AI P of I. Every such term should be non-zero for the whole thing here to be non-zero. And our terms are non-zero as soon as we have adjacency between the corresponding vertices in our graph. So we have to have adjacency between the vertices Vi and V sub P of I. So essentially it means that if we plot this kind of graph of a permutation P, which by itself is absolutely not related to our graph G, this is just a graph representing the permutation, and it's a directed graph. Still, we have something to say about GP and G. The term of the determinant, which is non-zero, we can get only if for every arc in graph GP from I to P of I, we have a corresponding edge in our graph G. So in particular, if we have, say, even this kind of trivial cycle, if this is I and this is P of I, still in our graph G, we should have an edge between vertex Vi and vertex V sub P of I. In this and only in this case, the corresponding term of the determinant for this permutation P will be non-vanishing. So now if we look at the graph GP and look at our graph G, for a non-vanishing term of permutation P in graph G, we should be able to see like these edges. And now let's look at this. If all the cycles in GP are even, so if we do not have triangles, pentagons, and so on, if we have cycles just of length 2, 4, 6, and so on, then in graph G, we can convert every even cycle into part of a matching. So to an even cycle of length 2 in GP corresponds just a single edge. And if a cycle is of even length greater than 2, then on every such cycle we can select a bunch of edges without common endpoints. And for every such cycle we take just every other edge, and the collection of edges gives us a matching. So if all cycles in P and cycles in a permutation are just the cycles of its directed graph, all the cycles in P are even, then there exists a perfect matching in G. Because in case of our assumption that we are now talking only about non-zero terms here, every cycle in P corresponds to a cycle of the same length or to a single edge in G, and cycles of even length greater than 2 can still be used to select a bunch of edges without common endpoints. And this argument can be reversed, so we can say that if G has a perfect matching, so if we are able to split all the graph vertices into endpoint disjoint edges, then we can construct a permutation of this sort, a permutation which is just a bunch of transpositions, where for every edge of the graph we take just the transposition of the corresponding elements. And it's easy to see that to such permutation there would correspond a non-vanishing term like this. So just as an example, if we have a matching of edges from V1 to V2, from V3 to V4, and so on from Vn-1 to V sub n, then the corresponding term here would be equal to x12 squared, x34 squared, through xn-1 n squared, with some sign, of course. So in the end, we can state the following. There exists a perfect matching in G if and only if there exists a permutation P such that this guy does not vanish and all cycles of P are even. And it turns out that actually after we take the sum of all these guys, the terms corresponding to permutation with odd cycles, they will make each other vanish. And all the terms corresponding to permutations with only even cycles, they will not vanish. So let's see why. Let's take some permutation P for which we had an odd cycle, say a triangle. And let's assume that I is less than j and less than k. Then the corresponding term in the determinant would be sine of p times various things related to different items, and then to this arc ij will have a corresponding variable x sub ij. For this arc, we'll have a corresponding variable xjk. And for this arc, as it goes from larger number to the smaller one, we'll have the corresponding variable minus xik. And now, if we take a permutation p prime, which is different from p, by just reversing this cycle, so j is mapped to I, and I is mapped to k, and k is mapped to j. It can be shown that if we reverse a cycle in a permutation, keeping its structure otherwise the same, the sign of the permutation is the same. So the sign of p prime is the same as sine p. Then we'll have the very similar terms. And then instead of xij, we would have minus xij. And instead of xjk, we'll have minus xjk. And instead of xik, we'll have xik without a minus. So we see that in the end, these two terms would be equivalent. The only thing they will differ in is their sign, which is determined by this thing because we have an odd number of terms here, and if we had an even number of terms here, then the signs of these two terms of the determinant would be the same. So we actually see that terms corresponding to permutations that have odd cycles in them, they can be paired in such a way that terms in the same pair kill each other because they correspond to the same product of variables just with different signs. And the terms that correspond to permutations with only even cycles, they do not kill each other, they reinforce each other. And in the end, it turns out that symbolically, the determinant of A can be computed as the sum just over permutations with only even cycles. For all the permutations that are different from each other just by reversing the cycles, one of the cycle or any combination of the cycles, they all will have the same sign of the monomials and they would all reinforce each other. And if permutations are comprised only of even cycles and do not differ from each other just by reversion of the cycle, but rather they have different contents of the cycles, so the cycles produce different partitioning of the graph vertices, then we would have different monomials here. We would have different combinations of variables here. And such monomials cannot kill each other. So in the end, this is not identical zero if, and only if, there exists such a permutation, and this permutation exists if and only if there is a perfect matching in our graph G. The algorithm thus for checking for the existence of a perfect matching in G would be just the same as for bipartite graphs. We are not computing the determinant symbolically, we are just replacing each xij with a random value, but be sure that if we put a random value here, then here we put minus the same random value, not a newly generated random number. Then we compute the determinant of this numeric matrix and check whether it's non-zero. And similarly bound the probability of an error according to the Miller-Lipton-Schwarzschild lemma.